Now we'll try to model. Now we'll try to analyze buckling using three-dimensional solid elements. So 3D deformable. Here we'll choose 3D. And our cross-sectional dimensions we'll consider, that is your 30 mm cross 2 mm. So here we'll create that cross section 0, 0, then 30 to the power minus 3, 2 to the power minus 3. Now this is the cross section, and we'll extend this one up to a depth of 300 mm, so 0.3. So this is the 3D model. Now property, we'll give the property of steel. Since it is not equal, we'll give the property of steel, that is your 200 GPa, 200 E9, and process 0.33. Now we'll define this is as a solid homogeneous material 1, and now we'll define now we'll assign the cross section. Okay, so we assign the cross section. Now assembly will create A instances. Now we can do the meshing. We can do the meshing in part or element, number of element here. We make this 300. And this size your 30. Along the depth we have to give at least 2 elements. Here we will give 4 elements. This side we will have 2 mm, at least 2 mm thickness, 2 mm thickness. So let us give 4 element. Fine. Other end also we have to give 4 number of seed value. Here we will give 4 seed value as 4. Okay, so let us see how many element it has created. 1, 2, 3, 4. Okay, so 4 element it has created. Now we'll do the meshing. So this is the meshing. This is fine meshing. Now we can define step. Next step we will assign what type of analysis we want to do. We want to do buckling analysis. So buckle will do here number of iteration we can make it 300, and number of eigenvalue we can make it 1. Okay, now what we can do, we can define the boundary condition. So here boundary condition, this end we will make as an end cluster option. This end we can use. Okay, this end we have selected whole region, and we are making U1, U2, U3 are 0. Okay, end cluster option we can do since in 3D solid element do not have any rotational degree of freedom, since in the C3D8R element do not have any rotational degree of freedom. So U1, U2, U3 represent your fixed condition. Okay. So this is that, and this end we have made the fixed condition. This end we provided fixed boundary condition. Okay. Other end, one end we have provided fixed boundary conditions. One end we have provided fixed boundary condition, and other end we provide displacement type boundary conditions. Other end we provide displacement type boundary condition, and here we here we can make U. Here what we can do, we can constant U1 and U2. Okay, U3, U2 make it free. Now we can apply the load as a pressure, and here we can apply the pressure magnitude considering as 1. Okay, so here you can see we have applied the load as a pressure. Now we can go for analysis. And so let us submit. If we observe there is some error is coming related to iteration, then you have to go to the step and you have to increase the number of iteration. So we have to wait for the solution and we have to see whether there is a error or warning. So from the monitor option you can check error or the warning. Till now it is fine. It is showing running. Again, it is saying that file processor completed successfully. So I hope there will not be any error. So let us wait for the result. Our eigenvalue is coming as 141 e to the power 7. So from this option, we can enlarge the size. We have to go to viewport and then you have to go for viewport annotation options, and from there you can check. From there you can select the set font and you can select this one and increase, and you can increase the size, okay, so that you can see it clearly. So here, what further you can do the conversion study by increasing number of element or by taking higher order element. Here we have used C3D8R element. You can have C3D20R element, C3D20R element, okay, and you can see whether you are getting converged result or not. But since we have used sufficient meshing, so I hope this result is very close to our converged result. One more thing you have to keep in your mind is that along the depth you should take some element along the depth. So we have 2 mm thickness here. So along the thickness you should have at least 2 elements, if possible to increase to 4 elements, at least 4 elements. So here we have taken 4 elements along the thickness. So I hope our result is here converged result. So we get our converged eigenvalue, that is 1.41 e to the power 7. Now buckling load is that your eigenvalues that we obtained here times buckling load factor. Okay, so how much load we have applied multiplies your eigenvalue is your actual buckling load. So we have got 1.41 e to the power 7, and apply load is your apply load we have given as a 1 unit pressure. So that pressure into the area will be your applied load. So area is your 30 to the power minus 3 times 2 e to the power minus 3. That is the area, and 1 unit load, 1 unit pressure we have applied. Now buckling load will be 1.41 times the load. Okay, now if we multiply that value, okay, if you multiply that value, so from the ABAQUS analysis, from the finite element analysis, we got our eigenvalue as 1.41 e to the power 7, and buckling and the load and the buckling load factor BLF, okay, buckling load factor or load, you can say buckling load factor, that we obtained 6 e to the power minus 5. So if you multiply both the things, okay, you will get the buckling load. Okay, the buckling load that is coming as 8.46 e to the power 2 to the power 2. That means 846 Newton. That is your buckling load. Okay, now if you consider theoretical value, so theoretical values is your pi square EI by L square. So L is your effective length. Now here critical job is here to find the what is the critical length. So your job is here to find the critical length. So for this case, you will observe that one end is fixed, okay, and other end we have only in the other end we have 3 degree freedom in the loading direction. Okay, on the other end we have 3 degree freedom in the loading direction only, and we have rested U1 and U2. Okay, since we don't have any rotational degree freedom in C3D8 element, C3D8R element, so we do not touch that value. Only we have rested U1 and U2 0 and U3 we make it free, and in the direction we have applied loading. Okay, now if you do that, you will observe that our effective length for this case is coming as your 0.7, that is corresponding to one end fixed, other end pin connection, like that. Okay. So here you can see the buckling shape as per fine level method and buckling shape as per theoretical one. Okay, it matches with the third conditions, not the fourth condition. Okay, you can see the buckle shape. Okay, so our effective length will be 0.7, not 0.5. Okay, in the cell element we have considered 0.5 because in that time we observed that buckling shape was matching with your fourth cases. Now here you can see buckling shape is matching with your third cases, so our effective length will be 0.7. Okay, so you will observe that our theoretical buckling load is coming 8.94 with the power basically 894, and as per our find element calculation it is 846. So if you want to calculate the error, how much error is coming, you can. So here you can see the error is coming 5%. Error is coming as a 5% error. Okay. Other thing what you can do, you can check other boundary conditions. Okay, you can check other boundary conditions. You can check other boundary conditions. What we can do, we will make one end fixed, other end free. So here the boundary, what we are going to do, we are going to make free other end. We are going to free the other end. Okay, so one end is fixed, other end is free. So for this case our effective length will be 1. Okay, and now we will try to see what is the theoretical value and what is your value coming from the finite element analysis. Okay, so let us give the run and we will see. We have to wait for some time. Okay, so here you will observe that first eigenvalue is coming negative, so that you don't have to consider. You have to consider positive, first positive eigenvalue. Okay, so here what we can do, we can give number of eigenvalue. Okay, you can increase the number of eigenvalue here. You can go to the step and you can increase the number of eigenvalue as 2. Okay, you can increase the number of eigenvalue as 2. Okay, and then you have to give the run. Okay, so you have to kill it. You have to kill it. You have to kill it. You can kill it. Okay, if you do not kill it, if you close the operation, it will create a log file, and you will not be able to submit the same. You will not be able to submit the same job. So you have to, in that case, you have to change the name and then you can submit. But since I have killed it, and I also changed that number of eigenvalue. Okay, so now I can submit the job again and I can see what are the eigenvalue are coming. Okay, what are the eigenvalue are coming. Again, you have to see that first positive eigenvalue you have to consider. And one more thing you have to keep in your mind. One more thing you have to keep in mind. You have to see the buckle shape. You have to see the buckle shape. Then only you will be able to judge that what should be the effective length for this case. You can see in the previous video we have considered cell element. Okay, when we have considered cell element, and when we fixed one end and other end, in other end we rested all the degree freedom except your loading degree freedom. In that case we have observed that our effective length is to be 0.5, but in case of solid element we have observed if we fixed one end and other end, in other end if we make only loading degree freedom free, okay, in that case our effective length is coming 0.7. So now in both the cases you have to see buckle shape and you have to match your theoretical buckle shape, theoretical buckling shape. Then only you will be able to find the effective length. Okay, then only you will be able to judge what should be your what should be your effective length, and you can match your calculation. So here we go to the result. Now here you just see first buckling value or eigenvalue is going minus value, so we will not consider that one. Okay. Okay. Now what we can do, we can go for second one. Here you can see that your second eigenvalue is coming 6.86 e to the power 6, 6.86 e to the power 6. And here you can see your buckling shape. Okay, this is the buckling shape. Now we can see, so our effective length is 1, and theoretical value is coming 4.38. Okay, theoretical eigenvalue or theoretical buckling load is coming 4.38, and abacus here eigenvalue is 6.86 e to the power 6, and load factor is same. So here you can get our 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 buckling load as per find element value. Buckling load as per find element method is 412, and buckling load as per our theoretical is 438. And here you can see that error is nearly 6%. So here you can see that error between your theoretical eigenvalue, theoretical buckling load, and buckling load coming from your find element model, okay, is in between 5 to 6%. Okay, so we have considered two boundary conditions, and we have seen that error is coming nearly 5%. Now, what we can do, we have to check how the buckling shape. So here you can see, if you see this third condition, one end fixed, other end pinned. Okay, so you'll observe that our buckling shape is different than the case 4. Okay, buckling shape are different in the case 4. So here in ABAQUS model, you also have to see how the buckle shape look like. So what we can do, we can change the boundary condition again. Okay. So here you can see the buckling shape as per find element method and buckling shape as per theoretical one. Okay, it matches with the third conditions, not the fourth condition. Okay, you can see the buckle shape. Okay, so our effective length will be 0.7, not 0.5. Okay, in the cell element we have considered 0.5 because in that time we observed that buckling shape was matching with your fourth cases. Now here you can see buckling shape is matching with your third cases. So our effective length will be 0.7. Okay, so like that we have to see from your experimental validation also. For your experimental validation also, you have to see how your buckle shape is coming as per your experiment, and how buckle shape is coming, how the buckling shape is coming, as per your theoretical or find element model. And you have to compare the buckling load for that buckle shape only. So I hope you get some idea. Next, what we can do, we can consider a wire element and or 1D element, and we can see how your buckling load, how much your buckling load is coming. Okay, we can consider your 1D element, and we can see how much your buckling load is coming. Okay, so what happened for that? What I did, I already make a wire element, okay, 1D element, and then I give the property. Okay, and I did assembly, and in the step I have provided your buckling analysis, and I have requested for two eigenvalues, and I also have done the meshing, and I also have provided that orientation also. And loading, here you can see I have provided 1 unit load, okay, 1 unit load as a compressive in nature, and we make other end as a fixed, one end, another end we will make fixed. Okay, that is encaster option, that is basically indicating your fixed boundary condition, and other end we have make only loading rejection free or other degree of freedom or restraint, and we have run the analysis. Once we run the analysis, here we can see the result. Here you can see our theoretical, our find element result, our find element buckling mode is coming 1756. Okay, our buckling load is coming 1756. So here again, what we have to do, we have to consider this is your theoretical buckling load. Theoretical buckling load is coming 1750, and our ABAQUS value is coming 1756. Theoretical value is coming. So our load also here For this case 1, for this case load is 1, for this case load is 1. Okay, so eigenvalue times 1 is your buckling load, and as per our theory, our buckling load is your 1750. Okay, and in this case again our effective length is coming 0.5. So here you can see, once we model it using cell element and 1D element, our effective length we have to consider as your 0.5, because here you can see the buckling shape. Here you can see that buckling shape very similar to our fourth case. Okay, so we have to consider fourth, if we have to consider the effective length of for the fourth cases. Okay, fourth cases for cell element as well as for your 1D element, you have to consider the fourth case for calculation of your effective length. Okay, in case of solid element, what we observe that buckling shape is coming similar to our third case, so our effective length will be 0.7. Okay, so this is the way you have to validate your ABAQUS result or your experimental result with your theoretical result also. So with your theoretical result, Okay, I hope you get some idea. Thank you.